Thank you very much. Thank you for everyone who is here. This is the last session. I understand that you are really wanted to go, but there are two options. One is that because this session have only two, so I have asked that maybe I can give a talk of 40 minutes, or I can do very fast. Just kidding. Okay. So my name is Tran Cao, and I'm giving the talk. So this is about the two epistemic forward search planner that we developed with with our student Tiep and Francesco Fabiano. So this is an outline of the talk. I'm give you the motivation of the work and discuss the related work more than and then describe the the background of the and give you a very quick system description and evaluation. And then I spend more time on talking about maybe the future work, because that's the part that is the most interesting part, I think. So to motivate the work, what we really want to develop in an epistemic planning system in multi-agent domains. So consider a very simple example here. We have three people in a room, A, B, and C. So A, B, and C here, A, B, and C. And in the middle, so there is a table on the room, and there is a box that is locked. Inside the box, everybody knows that there is a coin, but nobody knows that the coin is head or up or tail, like up or down with the head. One needs a key to open the box, and A is the only one who has the key, here, A here. And anybody can distract somebody on looking at the box, or signal somebody to look at the box or open the box and look inside, given that that person has the key and the box is open, so on and so forth. So the planning problem that we wanted to consider is, for example, one of these, like something like this. What needs to happen if A wanted to know whether the coin line head or tail up? He or she also wanted to let B know that she knows that fact, but wanted to let C to leave C in the dark. So she shouldn't know that. She shouldn't even know that she knows that. Right? So if you give this problem to somebody, they come up with a solution, something like this. First, A distract C, then she signal B to focusing on her, and then she opens the box and look inside. Of course, there are some assumptions that, like what she, but this is a very simple and intuitive answer to this planning problem. Why it is difficult? What are the difficulties involved here? Say, here the thing is that one of these main problem, key difficulty in this one is the reasoning about knowledge or belief of other agents. So, and then this example, for example, involve the common knowledge operators. That would require basically unlimited number of nested knowledge operators to represent common knowledge system. So let's see what are the challenges in this endeavor. Example. So there are two very basic challenges in this in the development of epistemic planning. One is representation and reasoning. The other one is the implementation. So in the first challenge, what do we need to have? If we wanted to develop, say, a forward search planner, we need to have certain notion of, like, state. What is this state? This state needs to represent the state of the world, and it also needs to represent the state of belief of the agents. And then we need to define the transition between these states, right? So that's basically the challenge in representation and reasoning. After we do this, we need to be able to, so here's an example of that. Like say, for example, if I have a state in that everybody is looking at the center, and A is the opening the box, then everybody would know that, everyone would know that the box is open. But if somebody does not pay attention, then that somebody would still think that the box is still closed, right? So that is that's a difficult part in this. And in implementation, we need to, if we wanted to, and in this paper, we're focusing on a source-based planner. So, well, we need to find a source algorithm for computing the solution, and then preferably we wanted to have heuristic because we know that source, so all this kind of planning system would not scale up without heuristic. So, how did people, what are the approaches that people have attempted? One, I would classify that as a dynamic epistemic logic-based approach. So in this approach, states are represented something like a graph, a directed graph like this, that look like as a cookie structure, which is basically a directed graph, and then there is some, you can see that this is a node, this is the state of the world, and this is a possible state that the agent thinks that it may be in, and then the linking, the direction, the connection between the state basically express the fact that an agent, if this situation, for example, in this situation, A, B, C do not know whether the coil line head up or tail. And then in dynamic epistemic logic, the idea is that action instances are represented by an action model. And an action model is very similar to cookie structure, where, and the thing is that, here I highlight the action instances, because basically it is a ground occurrence of an action in a particular situation. And then if we have this action model and we have this state of this cookie structure, then we can define what it calls the update model. Basically, it's an operator. It's an operator that takes an action instant, action model, and then a pointed cookie structure, and produce a pointed cookie structure. Okay. So with this, we then it looks very simple, right? But what is the difficulty here? The difficulty here is that nobody knows how I can do the problem specification. So the problem specification is what kind of action model do I have in the problem to solve, and what is the initial state that I have to start with, right? And then the second thing is, and the problem with the initial state is that if we represent the initial state in the way that we used to in classical planning or planning in a single agent, we would say that, okay, the initial state is some structure that satisfies a set of formula or a formula. But the problem with this is that even with only two agents, there may be infinitely many structures like this satisfying the same set of formula. So that is a problem, right? So, and we are aware of one work that is done by, I don't know how to say exactly the name, but Eckenser, right? That use the idea of generated plan with implicit coordination for fully coordinated. So the idea in that paper is that you have a PDDL-like domain, but you have multiple agents, and then they need to create plan, join plan together but there are certain coordinations that need to be done, and one need to reason about the knowledge of the other. So they use this idea not in this full description, but in certain setting, and do that. The majority of the work on epistemic planning in multi-agent domain does something different. here is that there are a variety of proposals to represent the set of formula, often some kind of approximation of the Kirchhoff structure that we're talking about. And then actions are represented in one way or the other, PDDL-like representation, and this new representation account for the belief change of the agent when the action is executed. So, and depending, and then the transition function is defined, of course, depending on the formulation that used to represent the state. There are at least 4 work that we have reviewed, and so in all of these, so the first one that we were, so Muse, how do I say your name? Christian, right? And the work of Hector and his student, and then there's people from the Sun University. So the limitation here is that like the majority of them require that the formula have the bounded number of nested belief operators. So and that creates problem because it will affect the scalability of the planning system, and also because of if you cannot increase the number of nested belief operators like to 10, 20, something like that. And the majority, so the first two paper basically translate the problem into classical planning and then solve using the classical planner, where these two systems basically implement specialized search algorithm. So what we do in this paper, is we develop the heuristic forward search, but we wanted to eliminate the limitation that what we use in our implementation is a language called MAL that provide a succinct and very compact specification of the problem. And it also includes one that description of the initial state where we can basically compute a set of initial states, right? So, but that is not our contribution in this paper. I will have to skip the part of this thing, but I will give you an example of how this specification look like. So we have the executability precondition specification, like this action can be executed only if this condition is satisfied. And then this is to describe the on-tick action, this is to describe sensing action, this is to describe announcement actions. And then there are two additional elements that basically describe the perspective of the agent when an action is executed. For example, the first one here say that A observe open A, meaning that the agent A would know that he himself executes the action A, right? And then for the sensing action, for example, A observes pick A, or B is aware of A is picking into the book if this is happening. So that's the kind of thing. So then we define, given the semantic of this language is specified, like the state is represented by the point key structure, and the transitions and the action, basically the action instances are computed on the fly. So you can calculate the action model on the fly. So here's an example where we have this, the case that if A opens the book when everybody is looking, it look like this. If A is opening the book, if when C is not looking, then it's going to be something like this. And then we basically, given that, we can make use of the update model and define the transition function. So that And then to specify the initial state, we use this finite S-phi theory to define the initial state. And so basically it has 4 different types of proposition or formula that we allow. And we can show that if we confine ourselves to this thing, then we will have, we can calculate finite number of initial states. And then here we go. So after that, everything is like the same. Like we can use forward search planning techniques to find plan, right? So we developed 2 versions of that. One is just simply breadth search, and then the second one is a heuristic one. We added that, and I don't have time to go over this, but we introduced a notion called planning graph in this epistemic planning system. The idea is the same, so you have multiple levels, but each of these levels now is a set of basically a set of simplified E-states or pointed key structure, and then that's how it goes. Yeah. And yeah, I'm sorry, I don't have a lot of more time, but this is how we can calculate that. We can show that with this simple planning graph, so we can estimate the shortest path, the short minimal distance to the goal, and we compare these 2 systems with it. But I think that maybe I don't need to bother you with that. So the idea is that even the breadth search planning system does pretty well. And this one shows that with the heuristic, things are getting better in difficult problems. So in conclusion, that we develop here, we describe the two planner, one with the heuristic and the other without the heuristic. So we introduce notion of the planning graph, and to calculate the heuristic in this epistemic setting. What I love, the source code is available on GitHub, so you can download it and play with it. And I would love for people to try with it and see it, because there's a lot of things that could be done next. But say, for example, we do not know how to check for repeated state. Well, it is something quite difficult because it update model makes the pointed key bigger. So a simple graph homomorphism is not going to work. And then investigating the use of this planning graph or some kind of planning graph would be interesting. And then the other thing is that in this paper, we limited ourselves to like truthful announcement. But in multi-agent setting, an untruthful announcement is even more interesting and more difficult to deal with. So with that, I wait for questions.
Thanks a lot.